So welcome. This is now the 8th lecture, I believe it is, and we're going to talk about inelastic magnetic neutron scattering. Maybe I should just mention that we are actually coming to you today from Japan, where I'm going there for a conference. And but I think everything should be smooth, and this is one of the virtues of using the internet. But we'll see if that remains a virtue after we complete the lecture. Okay, so the subject today is, as I mentioned, inelastic magnetic neutron scattering. And we're going to talk first about the features of the scattering cross-section. And in the process of doing that, I want to introduce the dynamic correlation function, which will be our central mathematical tool that we use to communicate the results and to discuss them, if you will, particularly with the theoretical community. We'll talk about some basic mathematical features of the dynamic correlation function, particularly the fluctuation dissipation theorem and various types of sum rules that help us. And actually, one of the main sort of points that I wanted to make in this lecture is that it's quite important for the experimental neutron scatterer to be well aware of these various mathematical parts, because experiments are sort of hard enough, and they typically have various problems and that we have to deal with, and the materials that we look at are very complicated, and so it's very good to have some really core aspects of the scattering that we measure that we know cannot actually be violated, in the sense of being violated and then still being a reasonable experiment. So what I mean here is that when we see that there are some problems developing in those areas that we know where we have real mathematical identities, then we ought to look at, is the detector measuring what it should be measuring, and is the crystal lined up correctly, and all sorts of extraneous experimental factors. So I want to put some emphasis on that today. And then I'm going to go in and talk about various examples of the use of inelastic magnetic neutron scattering to illustrate various of these points, and there'll be a summary at the end. All right, so first, talking about the inelastic magnetic scattering cross-section. And so it's listed in the sort of simplest form that has most of the relevant features in it on the top line. And just to sort of remind you how we got there, I want to remind you that we developed a general expression for the inelastic scattering associated with either the strong nuclear force or the dipole-dipole interaction. And in the case of the strong nuclear force, we actually ended up relating the inelastic scattering cross-section to a two-point correlation function that involved a phase factor, e to the iq r at time 0 and e to the iq r at some different time. And then we went through and did the multiphonon expansion, and we picked up the elastic term and the one phonon term. In the case of the magnetic inelastic scattering, in some sense it's actually easier, because in the dipole-dipole interaction, we end up seeing directly the appearance of the spin operator. So in a sense, you can say that the spin operator modulates the strength of the magnetic scattering. And so what we end up measuring without the need for having the step of a multiphonon expansion is actually this two-point spin-to-spin correlation function. And this, I think, is really the beautiful feature that makes neutron scattering so powerful in understanding the dynamic magnetic properties of materials. So I'm going to spend most of today essentially talking about the interpretation of data which can be considered to be measurements of this two-point dynamic correlation function. Okay, now I think it's the first time that I actually introduced this concept of the dynamic correlation function, and what it's really done is it has relegated into a certain mathematical definition, if you will, the most important part of the scattering cross-section. And so on the next line here, I've written out that expression for the two-point correlation function. And you'll see that it consists of a Fourier transform in time, which is this part, and a Fourier transform in space, which is this part of this two-point correlation function. And what I have here is spin operator component alpha, that could be x, y, or z, and component beta likewise. And it's evaluated at position L and position L prime, and there is a time that shows up because this correlator is a two-point space-time correlation function. And as we mentioned previously, we measure actually momentum transfer and energy transfer, and they become the conjugate variables to position coordinates and time coordinates. So we have to look at the information in Q omega space, but we have this expression to bring us back to real space and real time if we want that. Okay, so now getting into the features that we know for a fact about the dynamic correlation function. And one of those is the detailed balance expression, which I've written down here. And you remember we also derived that in the case of phonons, because that is a completely general result pertaining to inelastic scattering from material which is in thermodynamic equilibrium. And so that one is very important for us to keep in mind, and I think there might be examples of its use today as well. At this point, I'm just going to briefly look at my chat window to make sure that everything is still functioning okay, and then I'll get back to the next slide. So early good morning and so on. So if anyone has a question, I could also entertain a question posed on this chat window about any of this. Just hold on for a second, see if there are any questions. And I'd really encourage you to ask any questions as you go along, so we can have an interchange. Last week last Tuesday there was a good question about itinerant magnetism, which I thought was quite helpful. And actually, after the lecture, there were many good questions from my assistant there at the University of Toronto, but those we did offline. So please feel free to write your questions in. Otherwise, I'm going to continue. Okay, so let's see here. Come back to the next slide. All right. So for some useful exact sum rules I want to mention these first. And these are provided without a real proof, we have to say. And I'm still promising to give you some homework where you will explore some of that. But I thought in order to get through the material today, it was probably more useful for me to write these expressions out. And I'm going to say a few words about where they come from. So the first expression that I want to emphasize is the so-called total moment sum rule. And this is actually a general result from Fourier analysis. So remember that we have position coordinates relating to wave vector, time coordinates relating to energy transfer in a Fourier transform. And what the Fourier transform, the way this works, is that if I take a total integral over conjugate variables, in our case momentum transfer and energy transfer, then I actually end up relating to the equal time and equal position correlator. And this essentially comes out of the total integral of the phase factor e to the I x, with e to the I omega t, which becomes a delta function in time if I integrate over frequency, or in frequency if I integrate over time. So the total integral relates to the equal time part of the correlator and equal space part of the correlator if I carry out the integral over momentum space as well. So you see the result of that is that I end up relating this complete integral of SQ and omega to the dot product of the spin operator at the same time and at the same place in space. And note here that I've summed over the Cartesian coordinates or Cartesian indexes alpha in this expression. And of course that expectation value of the spin operator squared, as it were, is simply is simply the length of the, it's simply related to the total angular momentum squared, which is just s times s plus 1, as you see here. Now, you might ask, well, but how often are you going to have enough information to actually be able to carry out this complete integral of momentum and energy? And in truth, usually we don't have all of that information available. I mean, we will have an integral over some limited part of space, not all of space, not all of momentum space. And that's okay, because in a sense, this total moment sum rule, its main, should we say, virtue, is that it allows the experimentalist to develop this concept that if I have a system of spins interacting in some fashion, then the result of these interactions, from the point of view of a scattering experiment, is to distribute a certain fixed amount of intensity in specific and interesting ways through momentum and energy space. But it doesn't actually, there's nothing that has to do with the correlations between the spins or all the physics of the interacting spins that can change what is going to be the total strength of the overall magnetic scattering. That's what this expression tells us. And so there are many instances during experiments where this is very important and useful to keep in mind. Let me give you an example. If you, for example, you might be following inelastic scattering as a function of temperature. You're changing the temperature of your sample, and the sample undergoes some sort of phase transition. As a result of that, there may be a redistribution momentum energy space of the magnetic scattering. If you see magnetic scattering vanishing in some part of momentum space, then it will have to show up in some other part of momentum energy space. It cannot just vanish completely because of this sum rule. Let me give you an example. For example, if there is the appearance of a magnetic Bragg peak as a phase transition takes place, then that intensity which went into the Bragg peak has to come from somewhere. In other words, there must be somewhere else in momentum energy space where the intensity corresponding has been depleted. And so this concept, in some sense, is more valuable just to keep in mind. I just invite you to keep this expression in mind as you interpret and look at inelastic scattering data. In some cases, one can also actually carry out this type of integral over the data to check whether the normalization that has been done in the experiment is actually correct. I'll tell you that you can actually measure S of Q and omega in absolute units if you're very careful about carrying out a normalization of the data. And then you can use this expression to basically check if you got all the factors of 2 pi correct and things like that. So that's another potential use. But the main use is just to keep in mind that intensity is redistributed in momentum energy space. It doesn't just pop out of nowhere. Okay. So next is this expression for the so-called equal time correlation function. And this is, again, a pretty simple result out of Fourier transforms. So I've written here a definition of a new entity, if you will, which is what we call the equal time correlation function. And it's defined as the Fourier transform in position space of the 2-point correlation function between these spin operators at position L and L prime. And this equal time correlation function, again relating to what I said previously, can be associated with the energy integral of the full dynamic correlation function. So in a sense, by doing only the energy integral, we end up relating our result to the equal time correlation function. The energy integral brings us to time equals to 0, if you will. And so this is also quite a useful expression to keep in mind. In some cases, we can actually design experiments to specifically measure the energy integrated intensity to within some approximation. And in other cases, it's useful to, even if we don't have the full range of energies, to have some sort of partial measure of this equal time correlation function integrating over the range of energies that we have available, or we may want to integrate over some limited range of energies to obtain information about the equal time correlations associated with processes at in that particular range of energy transfers. So to give you a picture of what this equal time correlation function is, we could say that it is the wave vector dependence of the energy integrated. We can say that it is, in a sense, the Fourier transform of a snapshot of the fluctuating spin configuration. So if I have a paramagnet, for example, where spins are in some dynamic fluctuating state, if I was to go and measure the energy integrated intensity, then that's going to relate to, if you can imagine that, a very fast photographic image of the spin configuration in its otherwise fluctuating state. This is what we can measure with the energy integrated intensity. Now, the time scale that's involved in this is going to be related to how wide a range of energy transfer is available to me in the experiment. And so, if I'm integrating over a very wide range, then I can access. Then I'm, in a sense, accessing very, very short times in my measure of the equal time correlation function. All right, so that was the first step. Now the next step is a little bit more intricate, and I'm not going again through the full mathematical detail, but I want to give you a sort of hint of where this so-called fluctuation dissipation theorem comes from. And then I'm going to say a few words of its utility in interpreting data. And so I defined this time-dependent so-called response function. And this is phi with a subscript q as a function of time. Now, I'll say in most of what goes beyond this, wave vector is actually sort of a quiet variable. I'm not doing very much with it. It just is carried around all the time to sort of remind us that it's there. So that is maybe a simplifying factor as you look at these expressions. Let me say that this phi of t function, if you remember when we discussed, I think we were talking about phonons and inelastic nuclear scattering. I made a little sketch of such a phi of t function, and in a sense, this is our example of such a phi of t function in the case of magnetic scattering. Now, it's defined in a somewhat weird way. It's a thermal expectation value of a commutator of spin operators at different times and at inverted values of momentum transfer. Why did I do that? Or why is that done? That's because it turns out that if I Fourier transform this time-dependent response function in this particular fashion as indicated here, again, this is a bit of an intricate expression, then I obtain the so-called generalized wave vector and frequency-dependent susceptibility. So you're familiar with susceptibilities as relating magnetization to magnetic field. If I have a big susceptibility, then a large magnetic field will induce a large magnetization. And so this is the response function in the language of linear response theory. And it's generalized here to deal not only with the response to a uniform magnetic field, but to be able to deal with the response to a wave vector dependent magnetic field and to a time-varying magnetic field, a magnetic field which has an angular frequency omega associated with it. And so this is quite a complicated beast, and there are not many experimental tools that we have available to actually measure this function beyond neutron scattering. So a magnetization measurement, for example, done on some sort of maybe a physical properties measurement system, in a sense is measuring the some aspect of this generalized stability, but it's measuring it at a wave vector transfer of 0, corresponding to the uniform field, and it's measuring it at a frequency which is either 0 or maybe in the range of several kilohertz. So with neutrons, we can now access the full range of momentum transfer going into the full Pyrazine zone, And also we can access, through this fluctuation dissipation theorem, which is my subject here, we can access the frequency dependence up to the terahertz and higher and beyond regime. So that's the dynamic correlation function. I'll also mention that one of the reasons we like to bring it into our mix here is that the dynamic correlation function is something that theorists can and like to calculate. I don't know if they like to calculate it, but we like them to calculate it. And so it becomes sort of a language in which we can talk to a certain type of type of theories. Okay, so that's the time-dependent response function and the generalized stability. Now, how is it related to neutron scattering? It's related through the so-called well, it's related to the dynamic correlation as I'll now describe. And the first step here is again provided without proof that essentially the dynamic correlation function S, Q, and omega is related to a time integral of this time-dependent response function. It's sort of a Fourier transform, but not entirely, because this prefactor that comes out in front. And that relates in actually quite a beautiful mathematical development to the fact that S of Q and omega is a expectation value of a 2-point correlation function. And so it relates to the Fourier transform of the 2-point correlation function, but phi of t is actually an expectation value of a commutator. And it's as a result of this commutator that we pick up this factor 1 over 1 minus e to the minus beta h bar omega in front. Good, so now we have expressions which relate the generalized stability to a certain transform of phi of q, and also relating the dynamic correlation function to a certain transform of phi of q. So that means that these two functions are actually connected to each other, and they're connected through the so-called fluctuation dissipation theorem, which I've listed below here. So you'll notice that what's shown up is actually chi double prime of q and omega. What does that mean? That means the imaginary part of this generalized stability. So when we're talking about, let's say, when we're talking about the zero frequency stability, then you'll find that the stability is actually a real quantity. But as soon as we talk about finite frequency stability, then we have to be ready for a potential phase shift in the response to the time-dependent field. And that's what's reflected in having a real as well as an imaginary part to the dynamic correlation function. And as you can see here, the scattering as represented by S of Q and omega relates to the imaginary part of chi and Q and omega, which also is called the absorptive part, because that's the part that describes the transfer to or from the material of energy in the process of exciting it with a time-dependent field. So in a sense, there's a certain logic in S of Q and omega being related to the absorptive part of the susceptibility, because as we know, S of Q and omega itself relates to inelastic processes that transfer energy to or from the sample in the process of scattering. So there you have the expression. Let me, before I take some questions, please type any questions you have into the chat window. Let me just mention this prefactor here, g mu b squared, that showed up in the denominator. So this is really a matter of exactly how things have been defined. And in these notes, I have defined S of Q and omega to be a correlator between spin operators. So it involves just simply the bare spin operator, not the corresponding magnetic dipole moment. Whereas the generalized stability, by its nature, ought to be something which involves the magnetic dipole moment, and so there you do pick up, you should pick up this G factor. And so I included it in my expression for chi, but I didn't include it in my expression for S. And that means that in the translation between generalized response function and dynamic correlation function, such a factor of G mu B squared shows up. But I wanted to remind you, and this is quite important, that the magnetic scattering cross-section is related to... all right, so we come to the next slide. Okay, so this is sort of one of my my favorites. Again, we're in the realm of trying to bring out these fundamental features of the dynamic correlation function, and this is again essentially an exact expression that we use in many contexts, and I'll give you various examples of it. The first line here actually can be inferred from a line on the previous slide. So I'm just going to back off to the previous slide and remind you of that relationship between the dynamic correlation function S of q and omega and the time response function phi q of t. You see they're related by this Fourier-looking expression. And what I'm doing on the next line is essentially turning this expression inside out to make it into an expression for the time correlation function. And you can see how I would do that just by moving these things to the left side and then taking a Fourier transform to bring out this guy here. So that's what I've done on the first line of this slide. And then what one can do is one can take a time derivative of this entire expression. That means the time derivative of the left-hand side must be related to a time derivative of the right-hand side. Now, of course, the time derivative in general would be a time-dependent function, but I'm going to evaluate that time derivative exactly at time equals to 0. That brings out a useful aspect, as you shall see. So first, to take the time derivative of the left-hand side, that is done using the equation of motion for the Heisenberg operators, which you might remember relates a time derivative of the operator to commutator of the operator with the underlying Hamiltonian. And now, since phi of q itself is defined as a commutator, I end up with this interesting double commutator showing up. So you see that this commutator inside appeared because I was taking a time derivative of the spin operator. You remember that is the location where I have a time-dependent operator. So that's why in taking the time derivative, the commutator showed up, and then this guy just came along for the ride within the commutator. So it looks a little hostile, this expression, but that is what it is. You'll notice that there's no time dependence in it because I'm evaluating the derivative at time equals to 0. Okay, so then I'm going to take the time derivative of the right-hand side of that expression and evaluate that again at time equals to 0. And you'll see if I take a time derivative, I'm going to bring down a minus I omega, which gets multiplied by an I, so the minus sign goes away, and then there'll be now this omega d omega in my integral. And that's what shows up here. So this is a time derivative evaluated at time equals to 0 of the right-hand side of this expression. And then there's an interesting little manipulation here which involves the use of detailed balance, because this integral is a full integral from minus infinity to plus infinity, but you'll remember that s of minus omega is related to s of omega through the detailed balance expression. So you can actually relate this this integral with this parenthesis in there to what we would call a first moment integral over the dynamic correlation function. And here I see that kappa should have been a q. That's a little misprint in the slide. So this is why this sum rule, which I'm deriving here, is called the first moment sum rule, because it relates to the, in a sense, the interpretation of the dynamic correlation function as a probability distribution function that I'm using to calculate some sort of weighted average of frequencies. So if I have a lot of elastic scattering, then I'm going to be looking at I'm going to be I'm going to be getting from this, in a sense, some sort of averaged value of frequency of frequency in my inelastic scattering. If I have if most of the intensity lies at some high energy, then I'm going to find that this energy, this first moment, will end up producing for me that estimate of that sort of mean energy of the spectrum. So it's some sort of overall mean energy in the spectrum at that particular momentum transfer. But its importance here is that through this expression on the top, I end up with this lovely relationship between a first moment of S of Q and omega and an equal time expectation value of this double commutator. And you could say, well, why is this so useful? I'll tell you, it's useful because the right-hand side is actually not a very complicated thing to calculate. If you know the Hamilton operator, you can actually go through and calculate this thing, an equal time expectation value, and it really boils down to equal time local information about the material. So in many cases, it's relatively straightforward to pick up the right-hand side as long as I know something about the Hamilton operator. And the left-hand side is then something that I can imagine actually extracting from my experiment. And it's very useful for me to be able to relate the results of an experiment on a complicated material to some aspect which I can readily calculate knowing only the Hamiltonian operator. So all the correlated physics that might be involved in the magnet comes out in a relatively simple form on the right-hand side of the expression. Now I'll give you a couple of examples of the use of this first moment sum rule. Now I'm just going to check. I think maybe there was a question that appeared. Please, if you have a question, just type it in. No question so far. Okay, so I'm going to keep going. Okay. All right. So come to the next slide, and now I'm actually going to go into giving you a couple of examples of inelastic magnetic scattering, and I hope you've asked any and all questions that you had, because I'm going to now try to apply some of the results that I briefly summarized for you. Of course, the materials will vary, but I'm trying to illustrate certain features, and so I'm picking some relatively simple problems to talk about here. And the first problem involves, or the first material, not necessarily a problem, but the first material is copper nitrate. And this is a structure in which you have pairs of copper spin 1/2 degrees of freedom which interact antiferromagnetically. And these pairs are essentially decoupled from each other, but not entirely. So imagine instead of thinking about interacting spins in copper nitrate, we think instead about interacting pairs of spins. That's the nature of a dimerized system. And in thinking about it, it's useful first to write simply the to think about what happens when two spin 1/2 degrees of freedom interact antiferromagnetically. Well, they have a singlet ground state and a triplet excited state. And so the basic excitations that we're going to see are ones in which the neutron delivers angular momentum and makes a transition between a spin equals to 0 and a spin equals to 1 quantum state of this pair of copper atoms. But there are, after all, some interactions between the pairs, and this means that when I create a triplet excitation in one particular location, then it'll not actually remain fixed there. It'll want to move through the lattice in a process of, in some sort of coherent process, which will give rise to then a dispersion in the magnetic excitations. So I'll be able to deliver a certain amount of momentum to this triplet wave packet, which then moves through the system. And depending on how much momentum I deliver to it, I will have a varying amount of energy that I need to provide. And this will then give rise to a relationship between energy transfer and wave vector transfer. And what I've shown you in the picture here is what is measured in neutron scattering. Intensity is shown in this color scale, and it's shown as a function of energy transfer and wave vector transfer. And you can see that most of the intensity sits at an energy transfer of 0.45 millielectron volt. So that's the measure of the strength of the interaction between two copper atoms that form a single pair. If you will, the splitting between the singlet and the triplet level is 0.54 millielectron volt in the system. But there's some dispersion, as you see. The full bandwidth is approximately 0.1 millielectron volt. And then there's an interesting pattern of intensity that we were quite surprised about when we saw it first time. But it turned out that that was all very clearly understood in terms of these exact results for response functions. And so that's why this became my example to illustrate the value of this first moment sum rule in particular. So let me show you that little development on the next slide. Well, there was a little picture that showed up here, and that picture is an image of these interacting pairs of copper atoms, and the nature of the excitation being one in which I lift a singlet into a triplet state, and this triplet then moves along the spin chain, acquiring dispersion. So in the next slide, I'm using this first moment sum rule to develop a phenomenological expression, if you will, for the full inelastic scattering cross-section of the material. And this phenomenological model is then compared to the data below in these two images. On the left is shown the experimental data. On the right is shown the so-called single mode approximation. And what does that consist of? It consists of the statement that that the dynamic correlation function is some constant times a Dirac delta function. And you might say, well, where did that come from? But that's actually a pretty that's actually an expression of the it basically expresses that we have quasiparticles, and that those make up all of the scattering that we can have, and that those quasiparticles can actually be created and annihilated in a scattering process with the neutrons. When that happens, when there is such a well-defined quasiparticle which the neutron can create or annihilate, then we expect that the dynamic correlation function should take this form of just a constant times Dirac delta function. Now, I've written the expression as it would pertain at temperature equals to 0, because at temperature equals to 0, according to the detailed balance expression, which I hope you remember, then there cannot be any scattering at the negative energy side, right? Because there's no quasiparticle to annihilate when I'm sitting at t equals to 0. So that's why I wrote an expression which only has a finite value when omega is positive. Now, E of Q is some sort of dispersion relation for these quasiparticles, and we could develop various expectations for what that would look like, and we could also relate E of Q in various types of theories to the nature of the interactions in the system. But in what I'm writing here, I'm going to leave E of Q as some function that is part of our phenomenological model. Now, the key feature I want to emphasize is that sum rules actually link this prefactor and E of Q. Now, I wrote the prefactor as S of Q, and that's because it is actually equals to the energy integral of S of Q and omega, right? Because if I do an energy integral, the Dirac delta function is removed, and I just pick up S, this prefactor. And that is exactly what the equal time correlation function was. That is this prefactor that remains after I carry out a full energy integral. And so my statement is that the first moment sum rule will link S of Q to this dispersion relation E of Q. And it happens in the following form. S of Q, in the case of having a coherent mode of excitation, in that case actually becomes identical to this expression. So you notice I put in an omega here, so I'm using S of Q and omega as a distribution function, like a probability distribution function. And because my response function has this very special form, or has been postulated to have this very special form, then this integral is going to produce simply S of q times E of q. You can actually just easily carry out that integral, and you'll see that this approximate sign is actually an identity when we have this expression fulfilled. And then the numerator here, from the first moment sum rule, we can actually go and calculate this double commutator that I mentioned previously, and that produces this numerator up here on the top. And you'll see that it's actually a pretty simple expression in which I end up summing over pairs of spins, and I have what we could call a bond energy, which is the expectation value of a term in a exchange Hamiltonian. And then there is a wave vector dependent factor that shows up as a result of the nature of this double commutator. So here I employed both our definition of the equal time correlation function, and I employed the first moment sum rule to write down a relationship between S of q and the dispersion relation E of q. And so the upshot of all this is that as long as I can, if I have, if you will, a phenomenological form of E of q, then I'm able to write down a full expression for S of q and omega, because S of q is directly related to E of q in that form. Good, and so that is actually what we did in this case, and that ended up being able to fully describe the particular way in which the intensity of these modes varies through the zone. You can see that just drops out directly, and that becomes, in a sense, a relatively trivial aspect of the structural nature of the material, which is encoded in this prefactor here. So that was maybe a bit of a tall order, but it is to illustrate the way that in modern inelastic magnetic neutron scattering, people are using these types of results, mathematical results, to interpret and develop models for inelastic magnetic scattering. I'm going to just pause briefly to see if there are any questions so far in the chat window. I think it will be. Okay, so next example. I can see I'm going a little bit. I have to be a little careful with my time here. Okay. All right. So then I'm going to talk about, in some sense, the more standard examples of magnetic excitations. But I want to remind you that later, actually, I think it's one of the two last lectures will be given by Young Lee of MIT, and he's going to give you some more specific examples of spin wave excitations and their measurements in materials. What I'm doing here actually is just to, in a sense, I'm trying to juxtapose the more familiar cases of spin waves in ferromagnet and antiferromagnet with the next example, which I'm going to give, which will be a case where there are actually no well-defined excitations. So it'll be a pretty brief discussion of spin waves with the understanding that there will be a later, more complete discussion of that by Young Lee. So first, the case of spin waves in a ferromagnet. And in keeping with the general subject and the general gist of my presentation, I've written out the expression for S of q and omega, and it is the so-called transverse part of the scattering cross-section. There's no longitudinal part in a ferromagnet at very low temperatures due to a conservation law, and so we're looking at the transverse part of the spectrum. And it turns out that I can actually almost develop this expression without having to do any spin wave theory and just thinking about my conservation laws. Now, in the case of a ferromagnet, it's also pretty straightforward to do spin wave theory, and so you could follow either approach. But let me follow the case of relating this to the conservation, to the sum rules, etc., that I was describing previously. And the first thing I will note is that if I was to take a full wave vector and energy integral over this expression, then I would end up essentially getting simply a constant which is going to be proportional to S over 2. And let's just for simplicity think of the case of temperature equals to 0. So when temperature is equals to 0, then this term will actually completely vanish. And I only have, and this n omega, which is the Bose population factor, will vanish. And I just have this guy. So you can see that when I integrate over it, it'll just vanish. And I end up having a total integral of S, Q, and omega being related to S. We can argue about the halves and so on. I wouldn't, let's not get into that. But I wanted to emphasize that the strength of this inelastic part of the cross section it grows in proportion to S, the spin angular the spin quantum number. And you'll remember that the Bragg intensity, because we talked about elastic magnetic scattering, that the Bragg intensity varies as S squared. So the sum of the Bragg intensity and the inelastic scattering is S squared plus S. S squared plus S is also S times S plus 1. And we're very happy to have reached that conclusion because the complete integral over S of Q and omega, including the Bragg peaks, which I have not written into this expression, must be equal to S times S plus 1 in accordance with the total moment sum rule. So here you have a specific case where I can understand the nature of this prefactor because of the total moment sum rule. So that was my first little statement. The next observation I'll make is that there must be a ratio between the positive energy side and the negative energy side of the cross section, and that actually ensures that these prefactors must be as they are. This ratio of the neutron energy gain side prefactor to the neutron energy loss side prefactor, when I write it in the following form, does end up being e to the minus beta h bar omega as it must be. And then finally, there's an interesting point here, which is that for the ferromagnet, it turns out that the dispersion relation E of Q, which I've written down here, actually ends up being exactly proportional to that expression which we had for the expectation value of the double commutator. And so it turns out that the first moment wave vector dependence of the first moment of inelastic scattering for a ferromagnet is really equals to E of Q. And that means that the equal time correlation function ends up being simply a constant. And that's why in this expression you see that there's no wave vector dependence to the prefactor in the case of a ferromagnet. So, good. And so in that case, we really have these sharp modes of excitation passing through momentum and energy space. And in the case of gadolinium, it's a case of a system which has a basis. So it's not just I don't think it's just a simple Bravais lattice. And therefore, we end up with actually having several modes, and it's a bit more of a complicated story. My description was confined to the very simple case of a Bravais lattice. But that's what we would generally expect in a ferromagnet, sharp modes of excitation, and actually, also importantly, a quadratic dispersion relation emanating from the uniform gamma point. Now let me talk about the case of spin waves in an antiferromagnet. And a similar type of discussion can be held. Again, this is the basic form that we expect for the cross section. You'll see that there's now a more interesting wave vector dependence. This ratio of the expectation value of the double commutator, which I have on top, and the dispersion relation no longer vanishes as it did in the case of a ferromagnet. And so therefore you will now get some sort of wave vector dependence to the prefactor of that expression. And then otherwise, this prefactor of S half once again reflects the fact that the overall spectral density that we expect in the inelastic scattering should grow in proportion to S to satisfy the total moment sum rule. But then otherwise, again, I see this these two parts to my expression, which is the neutron energy loss side corresponding to the creation of spin waves, and the neutron energy gain side corresponding to the annihilation of spin waves. And if we were to go and measure this, then we would expect to see sharp modes of excitation passing through the zone, and we also actually end up with a linear dispersion relation emanating from the antiferromagnetic Bragg point. And the dispersion relation, as you see, is more complicated expression, which ends up being linear in the long wavelength limit. But again, this is going to be discussed in greater detail towards the end. Towards the end of the lectures by Young Lee. Now, what I'd like to do now is contrast these cases where the neutron was able to create and annihilate the underlying quasi-particles. I want to contrast that situation with a situation in which the underlying quasi-particle is not available to be created and annihilated in the scattering process. Because then something quite different actually happens. So I'm going to illustrate that with a little graph. And first, this is the familiar case that we just described, in which in the process of scattering, I create a quasi-particle. And then by tallying up the energy transfer and the momentum transfer, I can then trace out the trajectory of this so-called dispersion relation that characterizes the single particle process. Now, there's also the possibility that that there is no such single particle scattering process possible. And I'm going to give you a specific example of that. And in that case, there may be higher order processes possible in which pairs of particles are created. And this has a very sort of clear impact on the nature of the scattering cross-section, because now I can no longer control how much momentum is given to each of those two particles. All I can control is the overall linear momentum which is delivered. And this is what I've illustrated with this first line, that the overall linear momentum, I do control that by the difference between my incident and scattered momentum, but that doesn't tell me how much momentum went to the first particle and to the second particle. And likewise, when I measure energy transfer, I don't know how much energy went to the first particle and the second particle. And as a result of this, I'm actually not able, in these types of, for these types of scattering processes, to directly extract the dispersion relation for the underlying quasi-particles. However, I do obtain a bounded continuum of scattering. So for any given momentum transfer, there'll be some range of energy transfers that is possible given the dispersion relation for the underlying quasi-particles, EQ1 and EQ2. And this can actually be calculated if I know what those underlying quasi-particle dispersion relations look like. But actually the key observation I want to make is that when we look at our neutron scattering, inelastic neutron scattering data, we obtain a very clear and important message just right off the bat, which says that if we have this sharp trajectories through momentum energy space, then we're dealing with a single particle scattering process. Whereas if we have continua of scattering, and often a bounded continuum of scattering, then we're dealing with some form of a multi-particle scattering process. Now, of course, there are also some cases which are sort of in between these, and you could actually argue that most cases will be in between these, in which I both have access to a single particle process and also to some forms of multi-particle processes. But having discussed the single particle case, I'm now going to give you examples of the multi-particle case. And this example comes from one-dimensional magnetism, and I'm not going to go into too much detail about it, but I want to give you some sort of conceptual picture for what is the nature of the underlying quasi-particles. And so the physical system that I have in mind is a Heisenberg spin 1/2 one-dimensional antiferromagnet. In that system, if I flip a spin, how would I do that? That's some sort of mathematical process that I'm describing, in which you would consider a state which was fully antiferromagnetic, except for one flip which I somehow implemented. Then you'll find that if I then subject this state with a single spin flip to the time evolution operator, then you find the disintegration of the spin flip into two types of defects, which both are there's no change in energy of the system as that occurs, but you'll not be able to keep the spin flip together in one spot. And you'll notice that these defects actually represent a phase slip in an otherwise antiferromagnetic structure. And these turn out to be stable excitations, and they are the fundamental quasiparticles in the spin 1/2 one-dimensional antiferromagnet. Okay, so let me just see if there are any questions that have been posed so far. I'm just going to take a look at my chat window. So here I'm making a very important connection between the single quasi-particle dispersion relation. So this is the dispersion relation for the so-called spin-on excitation. Let me go back one slide and say that now I'm going to think about the dispersion relation for one spin-on. But it's very frustrating because I cannot create that spin-on in a scattering process directly. However, I can still think about its dispersion relation, and that's my object on the next slide. So here's the dispersion relation for this spin-on, and let's not talk about where it came from. We can note that it has the periodicity of reciprocal space, which is satisfying. But let's imagine that we knew that this is the dispersion relation for this spin-on excitation, and then let's think about what would be the nature of the two-particle scattering processes. And what I'm going to think about are processes that have momentum transfer of pi, and so momentum transfer is being measured in units of the reciprocal lattice vector, and I call that units of pi. And so this a process in which I take a quasi-particle from this location and move it to that location, that would have a momentum transfer of q, and the energy transfer would be very small because there was not much difference between the energy of this particle and the energy of the location that I place it into. So that would give me a low energy excitation. However, I can also go to a very high energy excitation, which lifts the quasi-particle all the way from down here to all the way to the top. That would give me intensity at that location. And then I can be somewhere in between. So the black, red, and green lines all have the same momentum transfer, but they're actually involving quasi-particles which have differing individual momentum transfer. And so this illustrates that in a two-particle process from a sort of a well-defined dispersion relation, I'm going to end up with a continuum of scattering in my inelastic magnetic scattering. And this is what I'm now going to show you experimental data showing you that to actually be the case. You could say, where is he going to get a spin 1/2 one-dimensional chain from, and how is he going to get enough intensity in his inelastic scattering trajectory to see that? It turns out that there are materials which are chemically three-dimensional. I mean, they really are crystal of a three-dimensional crystal, but there are very weak magnetic interactions apart from along the one-dimensional direction. And so that defines the magnetic chain direction, the direction along which the interactions are strong, and the interactions can be exceedingly weak in perpendicular directions. And these materials really do behave as one-dimensional spin 1/2 chains, and one can ascertain that by looking at bulk properties such as what I showed previously was specific heat, and what's shown here is magnetization data. Okay, now I'm going to show you the inelastic magnetic scattering from such a system, and these are data collected on a multi-detector triple-axis spectrometer. And again, I'm not getting into the technical details of instruments, but suffice it to say that here we are really measuring the energy and momentum dependence of scattering intensity. So really the full map of inelastic scattering is being measured here. And this is important in order to draw the types of conclusions that we would like to draw in this case. It's not enough to just say, well, here I have points on my dispersion relation. I need to see the full function of momentum and energy transfer to appreciate that here we have actually a bounded continuum of scattering. In the darker regions, there is no inelastic scattering above background, so no inelastic scattering above background here, nor down here. But then there's a certain region in energy at a given momentum transfer where there is inelastic scattering. And this is really the telltale sign of having a two-particle process, this kind of bounded continuum of scattering. And of course, there's a lot of intensity collected at the lower bound, and that's an important result, but that's not really a dispersive quasi-particle that I'm creating here, because this maximum is actually quite broad and much broader than my energy resolution. So this is an example of Newton scattering from a system in which I cannot actually create the underlying quasi-particle, but I can only create it in pairs. You could ask, why is it that you cannot create the underlying quasi-particle? And I'll give you a sort of a back of an envelope answer to that. It's because the underlying quasi-particle carries angular momentum of spin half, and so I'm actually not able to create it except if I was to deposit spin 1/2 to the sample. But I can't do that because I have to get the neutron back out again. So even though the neutron is a spin half particle, I can't actually create a spin 1/2 particle in the sample. I can only change the angular momentum by either 0 or 1. And so I need to have the neutron come back out again. And so in a sense, it's for that reason that I need to think about and only have multi-particle processes of scattering in the case of this spin 1/2 chain. I want to take it one step further regarding these spin 1/2 chains, and to show you an interesting result that occurs when applying a magnetic field. And this is maybe a little beyond what many of you would like to be able to follow, but okay, it's another example of really needing to look at the full wave vector and energy dependent cross section to obtain your conclusion. So the discussion follows on to the previous discussion of the zero field case. When I apply a field to the spin chain, what that corresponds to in the language of these quasi-particles is actually to shift the dispersion relation away from this magic point of half filling which I had previously. So what's happened is that I now have more quasi-particles which have energy less than the chemical potential, and which therefore are in an occupied state, if you will. I have more of those, and correspondingly the system becomes magnetized. In fact, the magnetization is carried by those extra quasi-particles which are added in response to the magnetic field. And now you can almost appreciate directly that I'm going to get some rather complicated features appearing in my spectrum, and it's because a wave vector transfer between quasi-particles which lie close in energy is now no longer exactly corresponding to a value of pi in momentum transfer. And because of the fact that all of this is living on a periodic lattice, this actually gives rise to both a low energy response at slightly positive values of at slightly larger values of wave vector transfer than pi, and at slightly smaller values of wave vector transfer than pi. So this deviation from pi being the lowest energy excitation causes some havoc in the nature of this two-particle bounded continuum. And this is what we expect to see, actually. It's sort of like becoming a little boss-eyed from what we'd seen previously as a result of magnetizing the system. And you can see that actually experimentally we end up seeing something akin to that. It's quite a complicated pattern that has now emerged, and we're now into a realm in which there's no sort of exact theory to really account for these things. Even though we're talking about a very, very simple system of interacting spin 1/2 degrees of freedom, once we apply field, we get into something which is actually quite interesting and complicated. And it's one example again in which I can't describe my excitation spectrum. Even at zero temperature, I cannot describe the excitation spectrum as being simply sharp dispersive modes of excitation. I have a continuum. It doesn't make it less interesting, it makes it more interesting. Okay, good. So I think that is where I think that brings me to the end of the what I prepared here. And just to summarize what I've said, and then I hope maybe there'll be some questions that I can look at after this summary. So get busy with your chat windows typing question. If you're in a classroom where there's only one computer with someone able to type on it, then maybe you can ask that person to type your question. And really any question you'd like will do. So here, first I'd say that inelastic magnetic scattering probes dynamic spin correlations. And of course we discussed that through this dynamic two-point correlation function that you saw on the first slide. The exact results that I reviewed in this presentation are very important for you to keep in mind, both as you plan experiments, as you conduct experiments, and as you interpret and analyze data afterwards, because those are really crutches that don't break, if you will. Even a very complicated system will have to satisfy these types of rules, and so it's important to keep those in mind as we walk through these experiments which are complicated and think about magnetic systems which are complicated. Then it's very helpful to have those exact mathematical results to work from. And then I wanted to emphasize that in many cases we want to really measure the full dynamic correlation function as opposed to just thinking about the dispersion relation. Certainly in the case of simple systems such as a ferromagnet, an antiferromagnet, with long-range order and so on, it might be adequate, and certainly it's an important first step to obtain the dispersion relation. But really there's more to it than that, and certainly the intensity associated with each point along the dispersion relation is important, because that gives access to what we call the equal time correlation function, which is this Fourier transform of a snapshot of the spin configuration. Also, and I didn't really talk so much about that, is that the width of the peaks in a system that has a quasi-particle that we can excite with neutrons, there may still be a width to this dispersive mode of excitation. In what I had written down, I always had a Dirac delta function, omega minus E of Q, but in general we would expect there also to be a width, and that width corresponds to a lifetime for the excitation. And that's a very important and interesting aspect to also probe and think about. And then finally, in some cases we have a broad continuum of scattering, and this actually reveals a multi-particle process of excitation, and in fact often the very most interesting systems, some of the very topical materials that people are thinking about now are ones in which the neutron does not create the underlying quasi-particles, but it creates it in pairs, or maybe even in larger collections than that. So with that having been said, take a look at these slides, which will be posted on the website. The information is also available in the, it's written up very nicely in the Lovesey book, and also, also actually very nicely in the book by Squires. I very highly recommend that one as well. And so know your sum rules and happy scattering. And then I'm going to just look at my chat window and see if there are some nice questions that I can answer. Okay, so I have a question from Mayun, and she says, she asks whether these rules are applicable only to hard matter, or can they also be applied to matter in liquid forms? And so that's a fine question, and the answer is that most of the expressions I wrote are perfectly fine also for non-periodic kind of softer forms of materials, and certainly liquids as well. But whenever I get to the point of wanting to using a periodicity of the underlying structure, some sort of static periodicity, then we depart. Then we become specialized in the case of crystalline materials. But actually, both the first moment sum rule, the total moment sum rule, and the equal time, the relationship between S of Q and omega and the equal time correlation function. All of those things apply perfectly well both to liquids and to hard condensed matter. It would be in the case where we write down the first moment sum rule, and it becomes related to this equal time expectation value of a double commutator. The evaluation of that double commutator becomes completely different in the case of the liquid as compared to the solid. So so yeah, it has generality. Any other questions? I see someone is typing a question, so let me see what that is. Okay. All right. It says. Okay, so it seems that I hope it's been reasonably clear, and thank you very much for your attention. As you can see, it's now becoming morning in Japan, so nice morning here in Japan. So I hope you have a good evening. Bye bye. Thank you.